Okay. Oop. See if that's better. How's that? Can you hear that? Back? Okay. Alrighty. So yesterday, what we did is we established the idea of an action potential. But we only got as far as talking about how we're changing the polarity on the membrane. So we'll start with negative charge on the inside, then we open the voltage-gated sodium channels, and the inside became positive. And then by opening the voltage-gated potassium channels, we could then repolarize the membrane. And that's as far as we got yesterday. It worked just fine in terms of an oscillator, changing the potential on the membrane. But it didn't give us very much information about how we're going to use that kind of a signal to send information over long distances. Remember, that's the function of the action potential. The function of the action potential is to be this all or nothing signal, which once generated begins to propagate along the conductor region of the axon. That conductor region now is loaded with voltage-gated sodium and potassium channels, and we can regeneratively open these over and over again to allow the potential to propagate from place to place. That's the long and the short of everything we're going to say today. And where we're going to start, though, is I'm going to postulate a situation, do a thought experiment, where we're only going to put the voltage-gated channels at one point of the membrane. And then we're going to ask the question, what happens if we open these voltage-gated channels, generate an action potential, and begin to propagate that action potential along the membrane? Now, what we'll find is that unless we have additional voltage-gated channels to regenerate that potential, the potential is going to decay in a matter of a few millivolts. And it's going to decay largely because of potassium leak channels carrying the positive charge out of the cell. We'll see that in biology, the distance over which one of these potentials could propagate is only a couple of millimeters. And so it's not a very useful long-distance signaling system. So what we have to think about is how we can use these voltage-gated channels, how we can distribute them in such a way that we can get the potential propagating over long distances. In the first iteration of the story, we're going to imagine that the voltage-gated channels are evenly distributed all along the conductor region. This is an example of an unmyelinated axon. In fact, I should write that out. Yes. We'll see that one of the impediments for rapid propagation of potentials along this membrane is something known as membrane capacitance. Now, membrane capacitance is a little foreign, so I have to spend a little time thinking about it and talking about it. And what we mean by a capacitor, and any of you have had some of this in physics, will recognize what we mean by a capacitor is an ability to separate charge across a non-conducting medium. If you think about a phospholipid bilayer with those phospholipid tails, it's a really remarkable non-conducting medium. And remember, it's really, really thin. It's only about 67 nanometers. And so we can stack up charge across this very thin non-conducting medium of the biological membrane. And so this is going to be a capacitor. And all on the membrane of these unmyelinated axons, we're going to see that these charges are lined up side by side all along the membrane. And this, in fact, presents a problem because when the voltage-gated channels open and the ions begin to come in, before they can effectively open the next set of voltage-gated channels, they have to discharge all that capacitance. So we'll see that in these unmyelinated axons, because of the membrane capacitance, we're really stuck with a conduction velocity of about 1 meter per second. And there are neurons that propagate at these slow velocities. But for the most part, it doesn't allow us a very rapid reaction time. You can imagine putting your hand in a hot stove and waiting 1 second for the information to get from your finger to your spinal cord, be processed through a synapse, and then wait another second for that signal to get down to your muscles to move your hand. Well, it's way, way too slow, so we need a much, much faster system. In vertebrates, the way we get the faster system is something called myelination. We've talked about myelination. Myelination are those fatty rings that have been deposited by the oligodendrocytes in the central nervous system and by the Schwann cells in the peripheral nervous system. We're now going to drill down, and we touched on this a little bit when we talked about glia, but we're going to drill down here and talk about why it is that by having segments of the axon surrounded by myelin and other segments naked, called the nodes of Ranvier, by clustering the voltage-gated channels of those segments where we have the nodes of Ranvier, we're going to see that we can increase the conduction velocity from about 1 meter per second to over 100 meters per second. Get a 100-fold increase. It's an interesting question of how that can be. How is it that we simply wrap these axons in an insulating layer and increase the conduction velocity by so much? And so what we'll see is that by wrapping the myelin around the internodal regions have a low capacitance. Because all this membrane separates the charge on the inside from the charge on the outside by this great distance, so they can't interact with one another. So now you have fewer charges along that internodal region to be dissipated by the ionic charges coming through the voltage-gated channels. Then the charge coming through the voltage-gated channel at one node is free now to propagate through the axoplasm to the next node and open the next set of channels. The next sort of mental gymnastics in here we have to think about is these ions are not going to walk from one node to the next. It's too far. What we're going to see is it's just the electromagnetic fields in the ions, which are acting as electromagnetic fields that are now propagating through the salt solution in the axon to reach the next node. And it's those electromagnetic fields now which are going to be opening the next set of channels. Because the conduction velocity of the electromagnetic field in the axoplasm is so rapid, the time between the sodium influx at one node and its electromagnetic field reaching the next node is almost instantaneous. And so we have very rapid movement of these electromagnetic fields from node to node, which then sequentially open the next set of voltage-gated channels. Sodium comes in, and again, we do this from node to node to node. And in that way, by propagating from node to node to node, using the electromagnetic fields on the ions, propagating through the salt solution inside the cell, we can increase propagation velocities to over 100 meters per second. And we'll talk our way through that. And then we'll finish with this idea of generator potential to action potential. And the example we'll use here is a touch-sensitive neuron out on the tip of your finger. You can imagine reaching out and touching something. And the way you initiate that signal is to generate something called a generator potential. The generator potential is the very beginning of that activity. The generator potential is the result of stretch-activated channels. Basically, these are channels that are opened by pulling on the membrane. They're unlike any of the other channels we've seen so far. You pull on the membrane, the ion channel opens and sodium comes in. Now, what distinguishes these from the voltage-gated channels is the more you pull on the membrane, the more they open. The more they open, the larger the polarization. So they're said to be graded with the strength of the stimulus. This is an important idea for generated potentials. We'll see again, it's an important idea for the neurotransmitter-operated channels, probably tomorrow or Monday. So then what we'll think about is the idea of using this generator potential produced by the opening of the stretch-activated channels, allowing sodium to come in. And we'll now use that sodium, that charge on the sodium, to activate voltage-gated sodium channels at the trigger zone, and again, begin the production of an action potential which now can propagate from the tip of your finger back into your central nervous system. So try to bring this thing full circle after describing the electrical events of making an action potential, propagating an action potential sort of in an imaginary way, and then bring it around to how we can propagate action potentials in neurons and how this is going to be a long-distance signaling system. As we get started here, let me walk through some slides that we had from yesterday, a little bit the day before. This is a summary of the idea of how we set up a membrane potential. This is a conceptual idea of setting up a membrane potential. Here in red is one of these potassium leak channels. The potassium leak channel didn't have to go down that far. I bet it goes clear to the top. Stop. Okay, screw it. So the potassium leak channels are always open. And what this is showing is that when we have these large negative anions in the inside, the potassium begins to run down its concentration gradient. Because remember, we have about 100 millimolar, 110 millimolar potassium in the inside, no more than 4 to 5 in the outside. So the potassium starts to run out, but it stops because the large negative anions will now hold the movement of those ions in check. So we've reached equilibrium. We've reached an equilibrium where the probability of potassium ion going out is the same as the probability of potassium ion coming in. And through the Nernst potential, we can now establish the value of that potential. Typically in neurons, it's about minus 70 or 80 millivolts. This is a picture I drew on the board yesterday. It's just a fancier picture of it. And what it's showing is an imaginary drawing of a voltage-gated sodium channel. The channel looks like this big tooth here. The protein looks like the big tooth. There's a channel down the middle. They're showing a gate here. So the sodium, which is about 130, 140 millimolar on the outside, and only about 10 on the inside, there's a tremendous driving force bringing the sodium from the outside to the inside through these channels. The only route for sodium to come into the cell is through these channels. Now, under normal circumstances, the gate's closed. But remember, we said the characteristic of this gate is it's voltage sensitive, it's voltage gated. So if we deposit a little bit of charge down here around the cytoplasmic side of the channel, that causes the gate to swing open. When the gate swings open, now we have a ready pathway for the sodium to flow down its concentration gradient and to polarize the inside of the cell. Now, these channels, these voltage-gated sodium channels, remain open only briefly, about a millisecond or so. And then, in a sort of stochastic event, the ball and chain moves up into the channel and plugs it. That's the inactivation gate. That's the inactivation case. So you've closed the channel. And remember, this will happen near the peak of the action potential because the action potential starts, the sodium comes in, the membrane potential seeks the equilibrium potential for sodium, but as we approach the equilibrium potential for sodium, those inactivation gates move into the channel and they stop the influx of sodium. They stop the permeability to sodium. And at that point, we begin opening the next set of channels we talked about, and these are the voltage-gated potassium channels. The voltage-gated potassium channels, again, are shown similarly here. Here's this tooth. It has a voltage gate on it. Normally, the gate's closed when the inside is negative. But when sodium comes in and delivers positive charge, that causes this gate to open. But unlike the sodium channel, which opens almost instantaneously, the voltage-gated potassium channel takes a while to open. It's slow. It's kind of a lumbering channel. So that's why it's called the delayed rectifier. But it opens, potassium flows out, and potassium now becomes the charge carrier, which carries the potassium, the positive charge out, returning the membrane potential back to its negative state. Again, you can think about this as moving charge. That's true, because we're moving charge in the form of potassium out of the cell. Or you can think about it just as equally by saying that the membrane potential seeks the equilibrium potential for the ion whose permeability is dominant. And when we've closed the sodium channels, inactivated the sodium channels, and opened the potassium channels, the voltage-gated potassium channels, the dominant permeability in this case is going to be to potassium. So the questions on that. So the next, yes?
So not for this one, but for the potassium-gated one, how do you know, or like how do you switch between the ball and chain being inactivating it and when it's closed?
So how, okay, great question. Let's go back. So the question here is, how do you manage to get the ball and chain out of the channel and then reopen and re-engage the gate? Well, one of the reasons the biophysicists want to talk about inactivation rather than closing is there are sort of two steps. The first thing that happens is the ball and chain moves in, and that will remain stable until you repolarize the membrane. And it's not until you repolarize the membrane that you can reset the position of the gate and move the ball and chain out of the channel. So you have to repolarize the membrane for the ball and chain to leave, and certainly to re-establish the position of the gate. Anything else? Well, this is a slide. I want to walk through this. And this is an important slide because you can understand what's going on in this slide. Put your phone away, I'd appreciate it. If you understand, don't look at me like that, just put your phone away. So So if you understand this slide, you have a pretty good idea of what's going on and what we've just been talking about. So what we're seeing in the black line is the change in voltage. That shows we start out at minus 60 millivolts. Now you notice there's a trick here. This is minus 60 millivolts, and that's slightly more positive than the equilibrium potential for potassium. We'll talk about that, why that is in just a minute. We start here at minus 60. Then we start opening the voltage-gated sodium channels. So the membrane potential now is going to go up. In this case, it's approaching plus 20. It can go as high as plus 40. That, again, is the membrane potential seeking the equilibrium potential for the ion whose permeability is dominant. So what we're seeing in the black line is the increase in sodium permeability, followed by an increase in potassium permeability, returning the membrane potential back down to rest. Now, there are two other lines in this figure. The two other lines represent the permeability to sodium and to potassium. So let's look at these each individually. In green, we have the increase in sodium permeability. So the increase in sodium permeability tells us as the channels are opening, we increase the membrane to permeability to sodium, depolarizes the membrane toward plus 40 millivolts. But then remember, the ball and chain closes the channel. It inactivates. And so now we reduce the permeability to sodium by closing the channels. But the red line shows the increase in permeability to potassium. And you'll notice that since this is in time, that the red line comes on much more slowly than the green line. The green line's almost instantaneous. But the voltage-gated potassium channels take a while to open. So they're the delayed rectifiers. So that during this period of time, the potassium channels are open and the dominant permeabilities to potassium, so it's driving the membrane potential back down toward the equilibrium potential to potassium. So the two subtleties in here, and if you see it, you really understand what's going on here. The first subtlety is that I mentioned in the beginning, is that the membrane potential here, the resting membrane potential, is set at minus 60 millivolts. The equilibrium potential, however, is between minus 80 and minus 70 millivolts. We blithely said that the equilibrium potential for potassium and the membrane potential are the same. Well, it's not quite true. And the reason it's not quite true is that all the time in these cells, these sodium channels are flickering open and closed. They don't stay open very long, and there are not very many of them, but they're flickering open and closed all the time. Well, if the sodium channels are flickering open and closed, what does that tell you about very slight changes in the permeability to sodium? Well, if they're opening, it's increasing the permeability. So that means as they flicker open and closed, we increase the permeability to sodium. So there's a resting permeability to sodium. And because of that resting permeability to sodium, even though the dominant permeability is to potassium, it's slightly depolarized. That's why the resting membrane potential is slightly depolarized from EK. It's because those sodium channels are flickering. The other thing you'll notice is that at the end of the action potential, there's this period over here where we get something known as a hyperpolarization. The membrane potential goes below the resting membrane potential. And it not only goes below the resting membrane potential, but it almost approaches the equilibrium potential for potassium. Well, why is that? Well, the answer resides in that red line. You notice the red line is the permeability to potassium. So you notice that during this period of time where we're approaching the equilibrium potential for potassium, the potassium channels are open. So they're driving the membrane potential toward the equilibrium potential for potassium. But at the same time, remember what's happened to the sodium channels. We've put them in the inactivated state. So there are many, many fewer sodium channels available to flicker open and closed. So in this state, we have lots of sodium channels flickering open and closed, but by the time we've inactivated them, or out here a few milliseconds after the action potential, we see that these sodium channels are closed and the dominant permeability is to potassium. So we're driving the membrane potential back down to the equilibrium potential for potassium. If you can follow that logic, if you can look at this figure and walk your way through all of that, you really understand how the action potential occurs. Doesn't tell you much information about how it moves, and that's where we're headed now, but it tells you how that occurs. Yes?
At like the resting membrane potential, like, are the sodium channels still like flickering?
Yes, the sodium channels are flickering open and closed at the resting membrane potential. And it's just when you get out here, you have fewer of them available to flicker open and closed because they're all in the inactivated state, or most of them. Let me take this one and I'll take you.
Just wondering where will the threshold be?
Oh, where would threshold be here? Good question. We're starting about -60. Threshold's probably someplace, about here, -55. -50, something in that neighborhood. So more depolarized than the resting membrane potential. And when we add enough positive charge one way or another, we get to threshold, off it goes. Yes. Wait, you first, then you.
What causes the flickering of the sodium voltage gauge? Is it just like a passing positive ion is enough to trigger it to open for a second?
So we think what's happening is there's just a certain amount of thermal agitation. And you'll line up you'll line things up so the channel opens, so the gate opens. You think it's just thermal activity. Yes?
Yeah, we mentioned last class about opening the threshold that all the sodium channels open up simultaneously.
Yes.
And we know that potassium channels open up slower.
Yes.
They also all open up at the same time?
And so the question here is, can we, from this figure, sort out the difference in opening times of when the times open for the sodium channels and potassium channels? And we can. You notice that the sodium channels open very quickly and come to a peak very rapidly, whereas the potassium channels take longer to start, and it takes much longer to reach peak. And because they don't inactivate, it also takes longer for them to close. The only thing that's closing these potassium channels is the change in voltage. There isn't an inactivation ball and chain on those. Anything else? Okay, so that's the idea of an action potential. But remember, why we have action potentials is to move signals from place to place in the nervous system. And where we want to start here is a hypothetical description. This doesn't happen in biology. Biology doesn't do this trick. But I like to tell the story from this point of view because I think it helps us understand why we need to have a distribution of voltage-gated channels. So what we're going to do is we're going to postulate a situation where voltage-gated channels are clustered. At one site. We can more or less draw this. We can lay out one of our imaginary axons where we have the two parallel lines representing the plasma membranes. And then we're going to put voltage-gated channels up here. And they will also be accompanied by their counterparts, the voltage-gated potassium channels. So these are the voltage-gated potassium channels. And the green ones are the voltage-gated sodium channels. Now, to have a membrane potential, we still have to have some leak channels. So all on the membrane here, we're going to put in our old friends, the potassium leak channels. And remember, they have the capacity to carry positive charge out of the cell. The next thing I'm going to do here is I'm going to make an imaginary case where we're going to put electrodes in. We're going to take measurements of the potential all along the length of this membrane. So each one of these sort of structures is meant to be an electrode that measures voltage. So we can imagine from the story we just told on those slides that in one way or another, and from yesterday's discussion, you may remember that we postulated this could easily be from synaptic potentials from ligand-gated channels, those that were operated by neurotransmitters. But positive charge arrives at the site one way or another. Remember what the positive charge is going to do. It's going to swing those gates open. And when it swings those gates open, sodium is going to come in. So the initial sort of priming here of positive charge gets the voltage-gated sodium channels to open their gates, and sodium comes in. If this is sufficient to bring the membrane potential to threshold, then down here, we can read the measurement of that potential. And what we would see is we'd start out at minus 70 millivolts or so. And then when we began to open these channels, we'd immediately go to plus 40 millivolts. The channels would inactivate. Voltage-gated potassium channels would open, would come back down again. So we'd see the full excursion of the action potential goes from minus 70 to plus 40, 110 millivolts. But what we're measuring here, all we're doing with this electrode is we're measuring the amount of positive charge. We describe that change in positive charge as a voltage. But in effect, what we're doing is we're simply measuring the amount of charge which has come into the cell. So let's take a measurement down here. If we take another measurement here, what we'll see is the membrane potential still is minus 70, but now the action potential, rather than going up to plus 40, maybe goes up to plus 10 and decays back down again. So the reason we have less charge at this site than this site is that some of the positive charge has flowed out through those leak channels. Because we have to have leak channels all on the membrane so that we can have membrane potential. What it's telling us is that these positive charges are going to flow out through the leak channels. And so at each successive station when we take this measurement, now where in the initial case we went all the way up to plus 40, here we go up to plus 10, maybe here we go to 0 millivolts. And we take another measurement, and we go from minus 70 to maybe minus 15 millivolts. And here we take another measurement, we go from minus 70 to maybe minus 60 millivolts. And here we go from minus 70 to maybe minus 69 millivolts. What I'm thinking about this is simply as the action potential tries to propagate along this membrane, the positive charge is leaking out through the potassium leak channels. So the amplitude of this signal is getting smaller and smaller and smaller. We can say that the amplitude of the action potential decays or decrements with distance. It's simply because the positive charge is leaking out of the membrane. Well, the distance over which this will actually occur, where we go from 110 millivolts down to maybe a fraction of a millivolt, this distance, if we didn't have other voltage-gated channels, this overall distance may be no more than 2 to 3 millimeters. Well, if we put this in some kind of context, we can imagine if we reach out and touch something. Well, if the signal were entirely dependent upon this kind of an action potential, we only opened the voltage-gated channels at the tip of our finger, and we didn't have any way to regenerate that potential, we would see that this potential would probably die out by the time it got to your first knuckle. It just can't propagate very far. So to have a proper signaling mechanism, what we need to do is regenerate this potential over and over again. How are we going to regenerate the potential and get it to propagate along the membrane? That's the next set of questions. So in the next panel, we can describe this as action potential propagation. In unmyelinated axons. You can read conductor regions. So how do we regenerate the potential? Well, simply what we can do is we can, again, draw the same concept, the same set of membranes, the same plasma membrane. We can, again, imagine voltage-gated channels up here. But now, rather than restricting the position of these voltage-gated channels to one region, we're going to distribute them along the membrane. Now, we'll intersperse some potassium channels along here too, because they will be grouped one with another. But what I'm trying to impress you with is that these voltage-gated sodium channels are going to be located pretty much at regular intervals along the membrane. And they will be accompanied by, I won't put all of them in, but they'll be accompanied by the voltage-gated potassium channels. And of course, interspersed among all of these, because we have to have a membrane potential, will be the potassium leak channels. So the blue is the potassium leak. The green are the voltage-gated sodium channels. And the red are the voltage-gated potassium channels. Let me get rid of this because I need to put my electrodes in here. So we're now going to put electrodes across the membrane and take measurements at regular intervals, just like we did above. So we can imagine putting electrodes in here. And we can imagine in one way or another, whether it's by injecting our own positive charge or by using synaptic potentials to deliver positive charge around those voltage-gated sodium channels. As we've said before, the positive charge now will cause the gates to open. And when the gates open, when these gates swing open, sodium comes in. Sodium is, of course, a positive charged cation, so it provides positive charge. This positive charge coming into the membrane now can be recognized by the next set of voltage-gated channels. So we take a measurement here. We see that we can start out at -70. We get a full-blown action potential because we have enough positive charge to exceed threshold and then repolarize the membrane. But when we take the next measurement here, because we also have a group of voltage-gated sodium channels in the same neighborhood, we start at -70, and we go up to +40 again. And we take another measurement, and we go from -70 to +40. And the reason we do this is that at each of these micro steps along the length of the axon, we can open a new set of voltage-gated sodium channels. So basically what we're doing is we're regeneratively opening the sodium channels, and we can imagine this wave of propagation, this wave of positivity propagating along the membrane. And it's always the same. It always goes to +40 millivolts and comes back down to -70 millivolts. So we repeat this potential over and over again by sequentially activating or opening those voltage-gated sodium channels. Yes?
So top ones maybe are they clustered to one side? Why are these ones not clustered to one side? Why are they different?
So what we've postulated here, see if I can answer the question this way. What we've postulated here is in the upper panel, an imaginary system where the voltage-gated channels are only at one point. And what I wanted you to recognize from that is that because the voltage-gated channels are only at one site, and because we can't open more voltage-gated channels because we don't have them, that positive charge will leak out of the membrane, and the potential will get smaller and smaller and smaller with distance. It decays or decrements. But here we don't have that problem because we've changed the arrangement of the voltage-gated channels. So now rather than only clustering the voltage-gated channels at one site, we've distributed them evenly all on the membrane. So we can now sequentially open these voltage-gated channels one after another. And by sequentially opening them, we can regenerate the action potential at each of these sites continually along the membrane. Does that straighten it out?
Yeah, that's right. So you're saying that top one is imaginary. That was more so we can understand the concept. That's all the facts of that.
The top one is conceptual. We don't really see that in biology because what we're trying to do with these voltage-gated channels is move this potential from place to place. And that just doesn't do a very good job of that. But this does a pretty good job. The problem with this one is we're stuck with a conduction velocity of in the neighborhood of about 1 meter per second. That's about as fast as we can make these action potentials propagate. And there are a couple of reasons for that. First is that we have to sequentially, in a rolling fashion, one after another, in baby steps, open these voltage-gated sodium channels. But there's a more substantive reason. And I want to let me put this in the backboard and then I'll come back to it. The more substantive reason comes from the concept of capacitance. And capacitance is defined as the separation of charge across a non-conducting medium. So let's lay that idea out. This, of course, is the phospholipid bilayer. It's remarkably thin. It's only about 6 to 7 nanometers. And yet, across this exquisitely thin piece of non-conducting material, the phospholipid bilayer, we separate charge. Because we said that the inside of the membrane is going to be at minus 70 or 80 millivolts. So all this negative charge is lined up on the inside. And then we'll have positive charges lined up corresponding to those negative charges on the outside. This very thin non-conducting region allows these positive and negative charges to approach one another remarkably closely. Each one of these charges has an electromagnetic field. The electromagnetic field is positive for these ions, negative for these. So these charges are being lined up one against the next, all on the membrane. So if we go back to this upper panel, if we think about the capacitance, all on this membrane, there are positive charges on the outside. Nope, it's not the one I want. It's true there, but all on the membrane, there are positive charges on the inside. Sorry, do it again. Negative charges on the inside and positive charges on the outside. It's because it's a great capacitor. To give it a number, for those of you who are in engineering, the capacitance of membranes is 10 to the minus 6th farads per centimeter squared. That's a pretty good capacitor. We can store a lot of charge across the membrane. But the storage of the charge isn't the problem. The problem we run into here is that when positive charge comes in through this channel, the first thing it has to do is offset the negative charge. It has to basically sop up or do away with that positive charge. So much of the sodium that's coming in through this channel is the energy in that sodium is going to be expended by offsetting the negative charge. We can't really effectively open the next set of channels until we've offset the capacitance. So this really slows things down. It just takes a long time here for the ions coming in at one site to offset the capacitance so you can open the next channel. And that's why we're stuck with about 1 meter per second. That should be an E. So where I'm going to go, yes?
I feel like you've already explained this, but what do you mean when you say like offset the capacitance? Do you mean like the difference between the negative and the positive?
So the positive negative, when the positive charge comes in, it has to, I don't want to use the word negate because it's a negative charge. It has to take the place of. So when I say offset, I mean this negative charge has to be replaced by a positive charge. And all of those negative charges have to be replaced sequentially by the positive charge. And then we can't, and the first thing we do in these small regions when we replace the positive charge is then begin to open the voltage-gated channels. We can't get a significant amount of ions moving through those channels until we offset those negative charges with the positive. So how do we solve the problem? Well, let me go. Let me do it here. We're now going to go back to what we talked about several days ago. And this is going to be the concept of a myelinated axon. And we're going to lay out, just as we did before, the image of the longitudinal view of the axon or conductal region. So here are the two membranes, again. But now the story is a little different because you remember from the story of the Schwann cells and the oligodendrocytes that after they've wrapped around the axon, they form these wrappings. But every now and again, every millimeter or maybe millimeter and a half along the length of the axon, we have those naked regions of plasma membrane. And those naked regions of the plasma membrane, of course, have a name. They're called the nodes of Ranvier. And to remind you again, these regions that are covered by the myelination, these are called the internodal regions. So these are the internodal regions. And these sites here are called the nodes of Ranvier. Now you may remember we said that the hallmark of the nodes of Ranvier is that that's the site where we cluster the voltage-gated channels. So unlike, let me deep six this panel. Unlike the upper panel, where the sodium channels are evenly distributed, we're now going to have voltage-gated channels, primarily the sodium channels, but along with some of their counterparts, the potassium channels. At the nodes of Ranvier. So these green channels, the voltage-gated sodium channels, are restricted, by and large, to the nodes. So let's think a minute what that means. Let's imagine, as we've done before, that we increase the positive charge around these sodium channels. So we increase the positive charge, and if we take a measurement, we see that the membrane potential depolarizes until it reaches threshold. And if it reaches threshold, it fires an action potential. And that action potential means that all of the voltage-gated sodium channels at the node open almost simultaneously and let the sodium come in. So you have a tremendous inpouring of sodium. You could imagine that these individual sodium ions had to take a walk down to the next node. You could imagine these are individual particles that had to diffuse down to the next node, but this distance is about 1 to 1.5 millimeters. Diffusion is going to be way, way too slow to do that. So how is it that these sodium ions coming at this node manage to affect these voltage-gated channels to the next node? The answer is each one of these sodium ions is carrying with it an electromagnetic field. So this electromagnetic field, the field is now propagating through the salt solution in the axoplasm, because the axoplasm is a salt solution with high conductivity. It's almost like a wire. And this salt solution now can allow these electromagnetic fields to almost instantaneously propagate. They don't have to move. The electromagnetic fields are now simply going to influence the next node. It takes a bit of thinking about this. You don't have to worry about these sodium ions arriving at this site. They don't. But their electromagnetic field can basically push negative charge out of the way and make this next site positive. So it's the electromagnetic field which almost instantaneously goes from this node to this node. The electromagnetic field moves from node to node. Almost instantaneously. I may have butchered instantaneously. So almost immediately, the next node feels the effects of the electromagnetic fields. That sodium channel opens, and we repeat this pattern over and over again. The final second, let me say, and I'll come back to this tomorrow, is that these internodal regions are a poor capacitor. And we'll come back to this idea of the poor capacitor tomorrow and why that increases the conduction velocity from 10 meters per second to over 100 meters per second. Dang it.
Question. So, do the anions that are like already there, do they play a role in carrying any of them?
They don't. The anions are said to be passively distributed, at least in this story. And you're right, there are lots and lots of chloride ions in there as well as the impermeant anions. But they are not part of this story. They're not part of the action potential story. Next week, we'll see that they play an important role in something called inhibition. And chloride, in fact, in many cases will flow in and maintain the membrane potential at a more negative state. And we'll talk about that when we get to that. And that's a synaptic potential, more than an action potential arrangement. But you're right. I blithely leave out the chloride. We don't have to worry about the chloride. It doesn't take part in any of this. We can do it all entirely through the impermeant anions and the voltage-gated sodium-potassium channels. Okay.
Hi, I just wanted to quickly ask, when looking at the plasmic solution, so it has a high salt, so the charge moves quickly through it, but not necessarily the sodium or the potassium and the